Similarly to how Nicholas Copernicus presented the heliocentric model, another dazzling correction in how we might interpret the universe could arise, starting a discussion known as the emergence of cosmology. This emergence is set apart by critical disparities in our estimations and comprehension of the universe's crucial properties, like its age, size, and pace of development. Neil deGrasse Tyson has noted that the discovery of the James Webb Space Telescope, JWST, has sparked this discussion with a picture that challenges material science. So, what precisely is this emergency, and how does the James Webb Space Telescope contribute to it? Well, contributing to it is a bit of a misrepresentation. It's more similar to a survey that has been in progress. The emergency refers to a place where how we might interpret the universe is challenged, especially regarding its age and size, which are connected by an extensive safety buffer. The presentation of the JWST has been pivotal in this setting, as we were previously limited in how far we could see into the early universe. However, with the JWST's further developed abilities, space experts can investigate considerably more distant worlds, giving us new perspectives on the universe and testing some of our past conceptions. This advancement allows us to peer further back in time, closer to the Big Bang, and observe galaxies as they were forming, which provides critical information that can either support or challenge our current models of the universe. To understand the emergency in detail, looking into the view is significant. The standard model of cosmology, known as the hot inflationary Big Bang model or lambda cold dark matter lambda CDM model, has been exceptionally successful in making sense of various elements of the universe, from gravitational lensing to the structure of the cosmic web and the development of galaxies. The lambda CDM model suggests that the universe began with a Big Bang, followed by a period of rapid expansion, and has been expanding ever since. It includes components like dark matter, which applies gravitational forces, and dark energy, which drives the accelerated expansion of the universe. However, each groundbreaking observation, particularly with instruments as cutting-edge as the JWST, raises the possibility that our current model might be inadequate or need to be updated. The lambda CDM model makes explicit predictions about the attributes and behavior of galaxies at various stages of the universe's history. For example, it predicts that galaxies in the far-off past should be smaller, less evolved, and contain fewer heavy elements compared to those we see in the nearby universe. This is because heavier elements are formed in the centers of stars and distributed through processes like supernova explosions, which take time to occur. The description you give is about how the standard model of cosmology predicts the movements within groups and clusters of galaxies, as well as the properties of the cosmic microwave background, CMB. As we travel back into the past, according to this model, galaxies should be smaller, bluer, less evolved, and poorer in heavy elements at astronomical distances greater than our own. This would lead us to expect to enter times of the universe without apparent stars or galaxies. However, researchers have found contradictory evidence that challenges these expectations, resulting in an emergency in cosmology. The emergency in cosmology centers on the uncertainty about the age of the universe. Different estimation strategies give various outcomes, leading cosmologists to struggle to accommodate these disparities. To attempt to address this issue, researchers use several techniques to measure the age of the universe. One of them is the study of cosmic background radiation, which involves unraveling the history of the expansion of the universe and using mathematical models such as the Friedmann equations, based on Einstein's theory of general relativity, to determine the expansion rate and thus the age of the universe at different times. The CMB, a remnant radiation from the early days of the universe, is a key tool for this calculation. Detailed maps of the CMB, like those provided by the European Space Agency's Planck mission, offer important information about the composition of the universe. However, these maps lack data on dark energy, a significant component of the current universe. Despite this limitation, researchers can use the Friedmann equations along with other observations to estimate the expansion rate of the universe at different times and eventually determine its age. The Friedmann equations describe how the universe expands, accounting for the density of various components like dark matter, dark energy, and regular matter. By analyzing the CMB, researchers can deduce the conditions of the early universe and extrapolate its evolutionary history up to the present day. Another approach to determining the age of the universe involves observing exploding stars, specifically type Ia supernovae. These supernovae act as standard candles, as they have a known intrinsic brightness. By comparing their known luminosity to their observed luminosity, astronomers can determine their distance and, therefore, the expansion rate of the universe at different times. This method, used in the 1990s, played a crucial role in the discovery of dark energy, which is now essential to cosmological calculations. It is particularly useful for determining the Hubble constant, a measure of the expansion rate of the universe. Although not exactly constant, the Hubble constant is instrumental in charting the expansion of the universe since the Big Bang, about 13.8 billion years ago. It has been observed that the universe has been expanding consistently. NASA has noted that the implications of this rate are significant. If the expansion is slowing down, it suggests the presence of an unknown force, perhaps dark matter, influencing this process. On the other hand, if the expansion rate is accelerating, it could indicate the presence and impact of dark energy, speeding up the universe's growth. In January 2018, researchers found something interesting. Although some telescopes showed that the expansion rate of the universe changed depending on the place of observation, the Hubble Space Telescope measured a faster expansion in the nearby universe, while the Planck telescope measured a slightly lower expansion in the more distant parts of the universe. This discrepancy in measurement highlights the vast size of the universe and reminds us of the pioneering work of Edwin Hubble, who first proposed the expansion rate of the universe in 1929. Hubble's observations of distant galaxies revealed that they are moving away from us, demonstrating that the universe is expanding. This discovery was one of the foundations of modern cosmology. Now, considering the expansion of the universe independently of your local region, you would observe the same phenomenon at the same speed as the Hubble expansion rate. Initial calculations were based on limited data. However, with technological advances such as the Hubble and Gaia telescopes, we have been able to observe more variables and refine our measurements. Different telescopes use readings of the CMB to calculate the constant, although this method has its limitations due to the availability of supernovae for distant observations, which limits our view of the universe. Since the discovery of dark energy in the 20th century, researchers have been stumped by the inconsistencies between these two approaches to the age of the universe and its expansion rate. As measurement technology becomes more accurate, smaller variations arise, driven by the development of more advanced systems. This progress, however, raises more questions than it provides definitive answers. Although the differences are minor, with just 10 to 20 million years separating the estimates, given that the universe is around 13.77 billion years old, it still warrants careful examination. One possible explanation for this discrepancy is the possibility of flaws in our measurements of the CMB. Despite being one of the most accurate measurements, it has been extensively tested since its launch in 2009 for validating its accuracy. Another perspective suggests a potential gap in our understanding of dark matter, raising the possibility that it may fluctuate over time and be linked to dark energy or some other unknown factor. This possibility has led to various experimental investigations. The accuracy of supernova measurements is also questioned, as the complexity of star explosions can introduce uncertainty into the models we use. Settling this uncertainty in supernova models could help resolve the disparity in measurements. This emergency in cosmology has been further exacerbated by the discovery of the James Webb Space Telescope. According to Neil deGrasse Tyson, the JWST found objects in the universe that challenge our current understanding. This means that our scientific understanding requires a complete update. However, the problem is that we have no idea where to begin to comprehend the extent of the scientific revolution. Let's take a look at the origins of the universe. Around 50 million years after the Big Bang, stars, black holes, and star clusters began to emerge, potentially even as soon as 50 to 100 million years later. However, these events should be relatively rare. What we don't know is how common galaxies evolved at later times, spanning events between 400 million years after the Big Bang. Ongoing JWST images reveal galaxies much more distant and therefore older than the standard cosmological model predicts. This disparity suggests that our model needs a major update. The discovery that the expanding universe relied on galaxies is a major development. JWST images show galaxies that formed much sooner than anticipated by current cosmological models, triggering a crisis in the field. This issue is related to galaxies and redshift, which is a common measurement in cosmology. According to the Standard Model, hydrogen began to appear 400,000 years after the Big Bang when protons and electrons combined, leading to hydrogen recombination. This changed the universe into a soup of hydrogen atoms with some helium and residual background radiation. The gravity of the radiation then acted on small fluctuations in this hydrogen gas, slowly pulling them together to lead to the first stars. These early stars, made mostly of helium and hydrogen, engaged in nuclear fusion, creating heavier elements like carbon and nitrogen. These elements played a crucial role in galaxy formation by absorbing heat and emitting cooling photons, which facilitated the coalescence of gas into galaxies. The process of galaxy formation and evolution is complex and involves many stages. In the early universe, gas was primarily hydrogen, but as time went on, the gas became enriched with heavier elements produced in the interiors of stars. This enrichment played a key role in the development of galaxies, as the heavier elements provided the building blocks for planet formation and life. The study of the first galaxies is a fundamental part of understanding the history of the universe. New observations, such as those made by the JWST, provide insights into the earliest stages of galaxy formation and can help answer important questions about how galaxies evolved over time. The question is whether the early universe was as chaotic as we currently interpret. As cosmologists push the boundaries of our understanding, they face a profound challenge in reconciling their observations with the theoretical models that have long underpinned our view of the universe. One of the most exciting and perplexing aspects of this ongoing investigation is the realization that the universe may be even more dynamic and complex than previously thought. Instruments like the James Webb Space Telescope, JWST, have provided startling insights into the early universe, unveiling galaxies that appear much older and more developed than models suggest they should be. This has shaken our confidence in the accuracy of current cosmological models and raised profound questions about the nature of the universe itself. In particular, one of the most intriguing discoveries made by the JWST is the observation of galaxies that formed only a few 100 million years after the Big Bang. According to the Lambda-CDM model, galaxies should have taken significantly longer to form, as the universe was still in its early stages of evolution during this time. The formation of galaxies requires the presence of enough matter and energy to facilitate the coalescence of gas clouds. And these new findings suggest that the processes we thought were necessary for galaxy formation may have been occurring much earlier than anticipated. This discrepancy raises a fundamental question. How do we reconcile these observations with the established timeline of the universe? One possibility is that our understanding of the early universe's conditions needs to be revised. Perhaps the factors that contribute to galaxy formation, such as the density of matter, the cooling of gas, or the role of dark matter, are not as we thought, and these processes may have been accelerated or even triggered by mechanisms we do not fully understand. This is where new theories may need to emerge, challenging the long-standing assumptions of cosmology. In addition to the JWST's contribution, there are other key observations that challenge our models of the universe's expansion. For example, the discovery of anomalies in the cosmic microwave background, CMB, radiation has raised questions about the consistency of our measurements of the universe's age and the Hubble constant, a critical value used to measure the rate of expansion. Different methods of measuring this constant have produced slightly different results, creating what is known as the Hubble tension. Some measurements taken from the local universe suggest a faster rate of expansion, while others, based on the CMB, indicate a slower rate. This discrepancy suggests that either the methods used to measure the expansion are flawed, or that there is some unknown factor affecting the rate of expansion. The Hubble tension is a particularly perplexing issue because it touches on fundamental aspects of our understanding of the universe. If we cannot accurately determine the rate at which the universe is expanding, then it becomes much more difficult to estimate its age, size, and ultimate fate. For example, some cosmologists have speculated that the presence of dark energy, an unknown force driving the accelerated expansion of the universe, might be responsible for these discrepancies. But if dark energy behaves differently than we currently understand, it could have profound implications for the fate of the universe, potentially altering its trajectory in ways we cannot yet predict. Meanwhile, other emerging discoveries, such as the detection of gravitational waves and the study of supernovae, continue to deepen our understanding of the cosmos. Gravitational waves, first predicted by Einstein over a century ago, are ripples in space-time caused by violent cosmic events like the merging of black holes. The observation of these waves has provided new ways to study the universe, allowing scientists to probe phenomena that were previously invisible to traditional telescopes. These discoveries, along with others, suggest that the universe is far more complex than we once imagined. Another area of growing interest in cosmology is the role of dark matter. While we have yet to directly observe dark matter, its presence is inferred from its gravitational effects on visible matter. Dark matter is believed to make up a significant portion of the universe's mass, yet its exact nature remains elusive. Some theories propose that dark matter might not be made up of the particles we currently understand, such as WIMPs, weakly interacting massive particles, but could be composed of more exotic entities. Exploring the properties of dark matter is critical to resolving many of the unanswered questions in cosmology, including the formation of galaxies, the distribution of matter in the universe, and the nature of the universe's expansion. Ultimately, the current era of cosmology represents a period of tremendous discovery and uncertainty. The tools we have at our disposal, including the JWST, allow us to peer deeper into the universe than ever before, revealing a cosmos that is more complex and mysterious than we had imagined. As new data continues to pour in, cosmologists will face the challenge of interpreting these findings and revising our models accordingly. In doing so, they will not only deepen our understanding of the universe's past, but also pave the way for new theories that may one day reshape our fundamental understanding of space, time, and the nature of existence itself.